Our universe might be missing half of itself. This is not about dark matter or distant galaxies, but something far more intimate, a hidden reality woven into the very fabric of our own. I am talking about mirror matter, a parallel world of particles that could be right here, right now, completely invisible to our eyes and instruments. By the end of this exploration, you will understand how a single broken symmetry in physics could reveal an entire shadow cosmos sharing our space. We will uncover why scientists hunt for disappearing neutrons and how silent stars made of ghostly matter could solve the dark mystery of dark matter. What does it feel like to question the completeness of everything you perceive? The key to this ghostly duplicate lies in a simple but profound idea: symmetry. In the mid-1950s, physicists believed the universe was fundamentally ambidextrous. They called this principle parity symmetry, the idea that the laws of physics should work exactly the same if you viewed the universe in a mirror. A reaction in a lab should proceed identically to its mirror image. It was an elegant, almost beautiful assumption. But in 1956, two brilliant physicists, Tsung-Dao Lee and Chen-Ning Yong, proposed a shocking heresy. They suggested that for the weak nuclear force, one of the four fundamental forces of nature, this mirror symmetry might be broken. The universe, they argued, might have a preferred handedness. The experiment to test this was conducted by Qin-Xiong Wu, and the result was unequivocal. The universe is not symmetrical, it has a left-handed bias. This discovery earned Lee and Yong the Nobel Prize, but it left a deep scar on the heart of theoretical physics. The universe felt lopsided, imperfect. So a question emerged: what if parity symmetry is not truly broken, but simply hidden? What if for every left-handed particle in our world, there exists a perfect mirror twin, a right-handed particle that we simply cannot see? This is the elegant proposal behind mirror matter. It suggests our universe is not incomplete but doubled. Mirror matter would be a complete parallel sector of particles, a cosmic looking-glass reality. Every electron would have a mirror electron, every quark a mirror quark, all interacting with each other through their own set of mirror forces, like gravity, electromagnetism, and nuclear forces, but completely invisible to ours. Think of it like two radio stations broadcasting on different frequencies in the same room. You can only tune into one at a time. Our atoms, our light, our detectors, they are all tuned to the frequency of ordinary matter. The mirror world operates on a separate channel, utterly silent to our instruments. This is crucial. Mirror matter is not dark matter, though it could be a candidate for it. Dark matter is defined by what it does. It exerts gravitational pull but does not interact with light. Mirror matter, by its very design, would do exactly that. But it is a specific, rich hypothesis, a whole hidden universe with its own chemistry, its own planets, perhaps even its own life, all forever ghosting through our own. The elegance of a symmetrical universe was shattered in a laboratory. For years, physicists held a quiet faith that nature's laws were perfectly mirrored, that the cosmos had no preferred left or right. This principle, called parity, was more than a mathematical curiosity. It was a bedrock assumption about reality's fairness. Then, in the mid-1950s, two theorists, Tsung-Dao Lee and Chen-Ning Yong, dared to question it. They proposed a startling idea that for the weak nuclear force, the force behind radioactive decay, this mirror symmetry might not hold. The universe, they suggested, could be fundamentally left-handed. Proving such a claim required an experiment of exquisite precision, and that task fell to a remarkable physicist, Qin-Xiong Wu. Her setup involved cobalt-60 nuclei, carefully aligned in a magnetic field at temperatures near absolute zero. The plan was to watch them decay. If parity held, the electrons ejected from the decaying nuclei would fly out equally in all directions, a perfectly symmetrical spray. But what Wu observed was a profound bias. The electrons had a clear favorite direction. It was as if the universe itself had a secret thumb on the scale, consistently pointing one way. This was not a minor fluctuation, it was a definitive violation. The mirror of nature, it seemed, was cracked. The discovery sent shockwaves through the scientific community, earning Li and Yong a Nobel Prize and forever changing our view of the cosmos. But for some thinkers, this broken mirror felt like a clue, not a conclusion. Why would the universe be built with such a glaring imperfection? What if the symmetry was not truly broken, but simply hidden from our view? Imagine a pair of identical twins who always move in opposite directions. If you could only see one, their world would seem lopsided, biased. But if you could step back and see both, perfect balance would be restored. This is the conceptual leap mirror matter makes. The parity violation we see in our world, the left-handed bias of the weak force, could be the signature of a complete, right-handed twin universe forever dancing just out of sight. The broken mirror in Wu's experiment may have been our first glimpse, not of a flaw, but of a hidden reflection. That broken mirror in the laboratory became a blueprint for a far grander design. In the decades following that pivotal discovery, physicists like Rabindra Mohapatra and others began to ask a revolutionary question. What if parity symmetry is not broken at all, but perfectly conserved in a way we simply could not perceive? Their answer gave birth to the mirror world hypothesis, a concept of breathtaking scope and elegant simplicity. The core idea is this: for every single particle that makes up our reality, there exists an exact mirror twin. For every electron dancing around an atomic nucleus, there is a mirror electron. For every quark bound inside a proton, there is a mirror quark. This is not a vague shadow. It is a complete, self-contained duplicate of the standard model of particle physics operating in parallel. These mirror particles would interact with each other through their own perfect set of mirror forces, a mirror version of gravity, electromagnetism, and the strong and weak nuclear forces. They would form mirror atoms, mirror molecules, and potentially mirror planets and stars, all governed by identical physical laws. Yet here is the crucial, mind-bending detail. These two sectors of reality are almost entirely invisible to one another. Our photons of light, the carriers of our electromagnetism, do not interact with mirror matter. Our mirror particles are blind to our light, and their mirror photons are blind to our atoms. The only possible bridge between the two worlds, the only whisper of a connection, is gravity. Both our matter and mirror matter would bend the fabric of space-time so they could feel each other's mass, but nothing more. It is a profound kind of isolation. You could, in theory, have a mirror planet pass directly through the Earth. The gravitational tug might be felt as a strange, fleeting anomaly, but there would be no collision, no explosion, no exchange of light or heat. The two worlds would ghost through each other, utterly unaware. This hypothesis restores a deep cosmic symmetry, not by fixing our lopsided world, but by revealing it is only one half of a perfectly balanced whole. The left-handed bias we observe is not a universal flaw. It is simply the signature of our particular slice of existence. Somewhere, in a realm forever tuned to a different frequency, a right-handed mirror universe unfolds in perfect harmony. This elegant doubling extends to the very forces that govern reality. In our familiar universe, everything that happens, from an apple falling to the fusion inside a star, is orchestrated by just four fundamental forces. Gravity shapes the cosmos on the grandest scales. Electromagnetism binds atoms and gives us light. The strong nuclear force glues atomic nuclei together, while the weak nuclear force drives radioactive decay. These are the four pillars of our physical world. Now, if the mirror hypothesis is correct, then the hidden sector must have its own identical set. There would be mirror gravity, mirror electromagnetism, and mirror strong and weak forces, all operating with the same strengths and rules, but exclusively for mirror particles. This creates a profound separation. A mirror proton would be held in a mirror atom by mirror electromagnetism, carried by a particle we could call the mirror photon. But here is the critical distinction: that mirror photon is completely invisible to our eyes and our detectors. It is the carrier of a separate, invisible form of light that only illuminates the mirror world. This means the two cosmic domains are almost perfectly insulated. The forces are twins, but they do not talk to each other. The sole exception, the one tenuous thread that might connect our world to its reflection, is gravity. Because gravity is not a force in the traditional sense, but a curvature of space-time itself, it is thought that all mass and energy from both sectors would warp the same shared fabric. A mirror star would have gravity that our matter could feel, and vice versa. Yet with no other interactions possible, this creates an almost ghostly relationship. You could have an entire mirror galaxy shining with its own mirror light, passing right through our Milky Way. We would never see its stars, never feel the heat of its suns, never collide with its planets. The only evidence would be a mysterious, unexplained gravitational pull, a massive presence that our telescopes see straight through. This is why mirror matter is such a compelling candidate for the mysterious dark matter that astronomers know permeates our cosmos. It fits the description perfectly: something with mass that exerts a gravitational pull, yet remains utterly dark and non-interacting with our light. The mirror photon, forever silent to our instruments, would be the reason why. The logical conclusion of this idea is as staggering as it is beautiful. If mirror particles can interact through their own mirror forces, then there is no reason they would not follow the same cosmic recipe that shaped our own universe. Gravity would pull mirror dust together, mirror atoms would bond into mirror molecules, and over cosmic time, these hidden ingredients could bake themselves into entire unseen worlds. Mirror matter could coalesce into mirror planets with mirror mountains and mirror oceans, and ignite into mirror stars, burning fiercely with mirror nuclear fusion in their cores. All of this could be happening right now, in the same galactic neighborhoods we observe, occupying the exact same points in space. A mirror solar system could be orbiting a mirror star at the center of our own sun's position, its planets phasing silently through the rock and gas of our familiar planets. The two realities would be like overlapping films, each telling its own epic story, completely unaware of the other. This raises a haunting question. If mirror stars exist, what would they look like to us? The answer is, they would look like nothing at all. A mirror star would not emit any form of light our eyes or telescopes can detect. Its energy would radiate away as mirror photons, invisible to our instruments. Yet it would still have mass, it would still warp space-time. So, to an astronomer, a mirror star would appear as a mysterious point of intense gravitational pull, perhaps distorting the light of background stars, yet utterly dark itself. It would be a perfect gravitational ghost. This is not mere speculation. It is a direct, testable consequence of the theory. Some of the strange, dark objects we infer from gravity alone, objects that do not match the profile of black holes or neutron stars, could in fact be the first evidence of this hidden cosmos coming into view. We may already be staring at a sky full of silent, shining mirror suns, seeing only their shadows on the fabric of space. That silent, invisible presence could be the answer to a cosmic riddle that has haunted astronomy for nearly a century. We call it dark matter, and it is the ghost in the machine of our universe. Galaxies spin so fast that the visible stars and gas within them should be flung apart, yet something unseen holds them together with immense gravitational glue. The light from distant galaxies bends as if passing through invisible lenses. The large-scale structure of the cosmos points to a vast, unseen scaffolding. All the evidence screams that there is far more matter out there than we can see, matter that does not emit, absorb, or reflect any form of light we know. For decades, physicists have proposed exotic particles as the solution, entities with names like WIMP and actions. But what if the answer is not a new, strange particle, but an entire hidden universe we have already described? Mirror matter fits the profile of dark matter with an almost unsettling perfection. By its very definition, mirror particles do not interact with our photons. They are completely dark to our electromagnetic force, yet they possess mass and therefore they exert a gravitational pull on the ordinary matter we can see. A galaxy could be filled with a halo of mirror stars, mirror planets, and diffuse mirror gas. This hidden mass would provide the extra gravitational grip to keep stars from flying away. It would bend light as it passes through, and it would seed the formation of cosmic structure, all while remaining utterly invisible to our telescopes. This is not just a convenient match, it is an elegant unification. The dark matter mystery and the broken mirror puzzle could be two sides of the same coin. Instead of inventing a new, hypothetical particle to explain the gravitational effects, we may be glimpsing the gravitational shadow of a complete, complex, and functioning parallel cosmos. Think of it like hearing the deep, resonant hum of a massive engine through a thick wall. You cannot see the machinery, you do not know its purpose, but you can feel its power and infer its complexity. The gravitational effects we attribute to dark matter could be that hum, the only detectable signal from a universe of mirror machinery operating just on the other side of a fundamental veil. This transforms dark matter from a cosmic placeholder, a simple missing mass, into something far richer and more profound. It suggests the darkness that binds our galaxies is not an inert substance, but a vibrant, dynamic reality with its own physics, its own history, and perhaps even its own forms of complexity we have only begun to imagine. But how do you search for a world you cannot see? You look for things that vanish. The first experimental hunts for this shadow reality did not aim telescopes at the sky. They focused on the quietest, most precise laboratories on Earth. Scientists realized that if the mirror world exists, there might be a tiny, forbidden door between our reality and its twin, a quantum crack in the wall. And the key to that door could be something incredibly simple, the humble neutron. Inside an atomic nucleus, a neutron is stable, but on its own, a free neutron is radioactive, decaying into a proton, an electron, and a neutrino in about 15 minutes. This is its known lifetime, but what if some free neutrons were not decaying at all? What if, instead of breaking apart, they were simply stepping through that quantum crack, transforming into their mirror twin and disappearing from our universe entirely? This process is called neutron to mirror neutron oscillation. It is a ghostly transition where a particle from our sector quantum tunnels into the mirror sector, becoming completely undetectable by any of our instruments. From our perspective, the neutron just vanishes without a trace. This meant that if you could measure the lifetime of a free neutron with exquisite precision in two different types of experiments, you might get two different answers. In a bottle experiment, you trap ultra-cold neutrons in a physical container and count how many are left after a period of time. Any neutrons that oscillate into mirror neutrons would hit the wall of the bottle, and because the mirror neutron would not interact with our matter, it would simply pass through the wall and be lost, looking exactly like a decay. But in a beam experiment, you measure the number of protons produced from neutron decays in a streaming beam. In this setup, a neutron that oscillates into a mirror neutron would keep flying right through the detection chamber, never decaying, and thus never being counted as a proton. If oscillation is happening, the bottle method should yield a shorter apparent neutron lifetime because it counts both decays and disappearances. The beam method should yield a longer lifetime because it misses the disappearances entirely. For years, this is exactly what the data showed. Bottle experiments consistently measured a neutron lifetime about 9 seconds shorter than beam experiments. 9 seconds is an eternity in particle physics, a glaring discrepancy that could not be easily explained by experimental error. It was a tantalizing whisper, a signature that something was making a fraction of the neutrons simply go missing. While recent, even more precise experiments have narrowed the gap and cast doubt on this being a clear signal, that original anomaly remains a powerful lesson. It showed scientists exactly where to look and how the most profound secrets of a hidden cosmos might be revealed not in the grand sweep of the heavens, but in the silent, meticulous counting of particles in a lab. That original discrepancy in neutron lifetimes was more than a measurement error, it was a potential doorway. To understand how a particle could simply vanish, we need to explore a strange quantum phenomenon already known in our own world: oscillation. The most famous example is the neutrino, a ghostly particle that barely interacts with anything. As neutrinos travel through space, they can spontaneously change their identity, morphing between 3 different types or flavors. An electron neutrino produced in the Sun can oscillate into a muon neutrino by the time it reaches Earth. This is not science fiction. It is a confirmed, fundamental property of the quantum world, showing that a particle's identity is not always fixed, but can be a shifting mixture of possibilities. Now apply that same quantum logic to the neutron. What if a neutron is not just a neutron? What if it is a quantum mixture of our ordinary neutron and its mirror twin? As it exists in our world, this mixture would have a tiny but finite probability of collapsing into its mirror state. When that happens, the particle would cease to interact with any of our forces. It would, for all practical purposes, vanish from our universe, stepping into the mirror sector. This is not teleportation, it is quantum tunneling between realities. The neutron does not decay, it transforms. From our perspective, trapped in our sector of forces, it simply disappears without a trace. The experiments designed to catch this ghostly transition are marvels of precision. One method involves trapping ultra-cold neutrons in magnetic bottles. These are not physical containers, but fields of magnetic force that can hold neutrons, which have a tiny magnetic moment in place. Scientists fill such a trap with neutrons and then wait, counting how many remain over time. Every missing neutron is a candidate, a potential escapee to the mirror world. Another method uses powerful nuclear reactors to produce intense beams of neutrons, monitoring their decay products with incredible sensitivity. The goal is to measure the neutron's lifetime, the 15-minute average, with an accuracy of fractions of a second. For years, the results from these different techniques stubbornly refused to agree. The bottle experiments consistently reported a lifetime about 9 seconds shorter. 9 seconds is a massive discrepancy in this realm of measurement, far larger than any estimated experimental error could easily explain. Where were those neutrons going? The most tantalizing explanation was that in the bottle experiments, a neutron that oscillated into a mirror neutron would no longer be confined by our magnetic fields. It would pass straight through the walls of the trap as if they were not there and be counted as lost, just like a decay. In the beam experiments, however, an oscillated mirror neutron would keep flying down the beam pipe, never decaying and thus never being counted at all. This would make the lifetime seem longer. The discrepancy itself was the signal, a fingerprint of a hidden process. While newer, even more precise experiments have complicated the picture, and the statistical significance of that 9-second gap has faded, the pursuit it inspired remains vital. It proved a profound point: the search for a parallel universe is not a matter of gazing wistfully at the stars. It is conducted in the silent, ultra-cold vacuum of a lab, in the meticulous counting of particles that might, just might, be slipping through the cracks of our reality. If a mirror world truly shares our space, its influence must reach into our own cosmic backyard. The search for this hidden matter is not confined to distant galaxies or sterile laboratories. It extends to the familiar rocks and worlds of our solar system. Could some of the celestial bodies we have catalogued, the asteroids tumbling between Mars and Jupiter, or the enigmatic moons orbiting distant planets, actually be composed of mirror matter? From our perspective, they would appear as perfectly normal objects detected by their gravitational pull on spacecraft and other planets, but they would be utterly dark to our telescopes. An asteroid made of mirror rock would reflect no sunlight, absorbing no radar signals. It would be a gravitational ghost, a massive presence revealed only by the way it tugs on the paths of nearby probes or comets. This offers a potential explanation for some of the odd, unexplained gravitational anomalies that occasionally perturb spacecraft trajectories, subtle nudges that suggest unseen mass lurking in the void. Perhaps the most startling possibility is the idea of a mirror meteorite. Imagine a small fragment of this hidden world, a pebble or boulder of mirror rock hurtling through space. If such an object entered Earth's atmosphere, what would we witness? The answer is almost nothing, at least in the conventional sense. A mirror meteorite would not glow from atmospheric friction because its atoms would not collide with the molecules in our air. There would be no fiery streak across the night sky, no sonic boom from a shockwave. The object might pass straight through our atmosphere and even through the solid ground beneath our feet, interacting only through the faint whisper of gravity. The only sign of its passage might be a minuscule, localized tremor, a tiny blip on a sensitive seismograph with no apparent cause, or a fleeting, inexplicable distortion in a carefully monitored gravitational field. It would be the ultimate cosmic ghost story, an impact without a collision, a visitor from a parallel reality leaving only the faintest ripple in our own. This thought experiment underscores the profound isolation of the two sectors. A chunk of an alien world could phase directly through our planet, and we might never know it was there unless our instruments were tuned to detect the most subtle of gravitational size. It transforms the space around us from an empty stage into a potential crossroads, where two separate realities perpetually intersect in silence. The hunt for these vanishing neutrons continues in laboratories colder than deep space. Scientists are now building exquisitely sensitive traps, not just to count neutrons, but to listen for the quietest of quantum whispers. One of the most promising experiments involves storing ultra-cold neutrons within a powerful magnetic field, creating a pristine, vibration-free environment where even the slightest anomaly can stand out. The goal is to measure not just the neutron's lifetime, but its behavior with impossible precision. If a neutron oscillates into its mirror twin, the process should be influenced by magnetic fields. A mirror neutron born from our own would be affected by the mirror version of magnetism. Any magnetic field in our lab could theoretically have a counterpart in the mirror sector, a parallel field influencing the hidden particle. This creates a subtle signature. By carefully manipulating our magnetic fields and watching for changes in how many neutrons disappear, researchers hope to catch the transition in the act. It is a bit like trying to hear a single instrument change its tune in a silent room by gently altering the acoustics of the room itself. To achieve this level of sensitivity, these experiments rely on a tool of astonishing accuracy, the atomic clock. Modern atomic clocks are so precise they would lose less than 1 second over the entire age of the universe. In the context of the mirror matter search, they are not for telling time, but for measuring incredibly small energy shifts. The core idea is this: if a neutron is quantum mixing with its mirror state, its energy levels might be minutely altered by the presence of a magnetic field. By using the stable tick of an atomic clock as a reference, scientists can probe the neutron's internal quantum properties, looking for a tiny, telltale wobble that has no other explanation. It is a search for a ghostly fingerprint on the fabric of reality itself. This pursuit takes an even stranger turn when we bring antimatter into the picture. Every particle we know has an antimatter counterpart, identical in mass but opposite in charge. Physicists have long studied how matter and antimatter behave in magnetic fields, a property known as their magnetic moment. If the mirror world exists, it might not just duplicate our matter, it could include mirror antimatter as well. This opens a fascinating new window. Researchers are now planning experiments to compare the magnetic properties of trapped antiprotons or anti-hydrogen atoms with those of their ordinary matter twins with unprecedented precision. Any infinitesimal discrepancy between how matter and antimatter interact with a magnetic field beyond what the standard model predicts could be a beacon. It might signal an interaction not from our world but from a hidden one, a fleeting exchange where an antiproton briefly feels the tug of a mirror force. We are no longer just waiting for particles to vanish. We are building instruments delicate enough to feel the draft from a door we cannot see as it opens into another universe. This elegant symmetry presents a profound cosmological puzzle. If the mirror universe is a perfect copy of our own, born from the same explosive origin, then logic suggests the Big Bang should have created equal amounts of both. The cosmic ledger should balance, with our world and the mirror world each holding 50% of all existence. Yet everything we observe, every star and galaxy in our sky, is made solely of our kind of matter. Where is the other half? If mirror matter is real, why does our sector seem to dominate the cosmos we can perceive? This is not a minor detail. It is a fundamental challenge that the theory must answer, and the solution lies in the first chaotic moments after creation. Physicists propose a process called asymmetric reheating. Picture the universe just after the Big Bang, not as a ball of fire, but as a seething, energetic field, a primordial soup containing the potential for both realities. As this field began to cool and decay, releasing its immense energy, that energy did not distribute itself evenly. Think of two rooms connected by a narrow hallway with a single heater placed just inside one door. The room with the heater becomes much warmer while the other remains cool. In the early universe, something similar may have happened. Our sector of particles, through some slight quantum preference or a twist in the unfolding physics, coupled more strongly to that decaying energy field. It got the lion's share of the heat while the mirror sector received only a faint remnant. This imbalance in energy or reheating had a dramatic consequence. Energy and matter are two sides of the same coin. With more energy, our sector could produce a far greater abundance of particles. The mirror world, receiving less heat, produced far fewer. The perfect symmetry of the laws was broken not by the laws themselves, but by the initial conditions, by how the energy of creation was divided. The cosmic scale was tipped from the very beginning. So, while the two universes are governed by identical rules, they started with vastly different budgets. Our sector, flush with energy, forged the countless stars and galaxies we see today. The mirror sector, operating on a fraction of that initial capital, might consist of a diffuse sea of particles, or perhaps it managed to form only sparse, dark structures. This explains why we are not swimming in a 50-50 mixture of both kinds of matter. We inhabit the privileged, warmer room of the cosmic house, while our mirror twin exists in a cooler, darker, and far less populated wing. The silence we perceive is not emptiness, but a universe living on a different scale. Its faint gravitational touch the only hint of its vast, quiet presence. The most profound question this hidden cosmos raises is not about stars or particles, but about life itself. If the laws of physics are truly identical in the mirror sector, then the same chemical pathways that led to life here should, in principle, be possible there. Mirror atoms would bond using mirror electromagnetism, forming mirror water, mirror carbon chains, and mirror amino acids. The elegant spiral of mirror DNA could theoretically assemble, storing information in a molecular language perfectly translated by mirror ribosomes. On a mirror Earth bathed in the invisible light of a mirror sun, an entire biosphere might have evolved in total silence, its forests growing, its creatures moving, all completely phased through the ground we walk upon. This is not a separate planet in a distant star system. It is a parallel layer of reality occupying our exact coordinates. A mirror whale could be swimming through the rock beneath your feet, while a mirror bird flies through the space where your ceiling is, both utterly unaware of the other's solid world. The philosophical weight of this idea is immense. It challenges our most basic assumptions about existence and uniqueness. We look up at the night sky and wonder if we are alone in the universe, while the answer might be that we are perpetually accompanied, sharing our home with a form of life so alien in its interaction yet so familiar in its foundation that we are forever blind to it. Scientifically, the implications are equally staggering. Evolution on a mirror Earth, subjected to the same gravitational forces and similar planetary conditions, might produce startlingly parallel forms. Mirror predators and mirror prey could engage in an endless dance of survival, their forms perhaps echoing the shapes of our own animals, converged upon by the same evolutionary pressures. Yet there is a haunting limit to this parallelism. Without any exchange of energy or information, the two biospheres would be on entirely independent historical paths. A random mutation, a missed meteorite impact, a different climate shift, any tiny divergence billions of years ago would cascade into a completely different present. Their world might have no mammals, or its dominant intelligence could be something utterly unlike a primate. The silence between us is absolute. We could not hear their calls, smell their blooms, or ever witness their art. Their entire civilization could rise and fall within the stone of our mountains, and we would register only the faint, constant pull of their planet's mass. This transforms the cosmos from a lonely expanse into a place of infinite, intimate strangeness, where the miracle of life may not be a single accident, but a melody playing simultaneously on two instruments that can never hear each other's song. That absolute silence between worlds is built upon a fundamental difference, a flipped signature at the very heart of matter. In our universe, the weak nuclear force has a distinct left-handed bias, meaning particles like electrons emitted in radioactive decay show a preference for spinning in one direction. This is the broken parity we observe. In the mirror sector, to restore the overall cosmic symmetry, the mirror weak force would have the opposite bias. It would be right-handed. This single foundational flip has a cascading effect on the building blocks of that hidden reality. It means that mirror protons and mirror electrons would themselves have opposite intrinsic parity or handedness compared to our own. Think of it like the difference between a left-handed glove and a right-handed glove. They are made of the same materials, they have the same structure, but they are mirror images that cannot be superimposed. This molecular handedness, known as chirality, is not a trivial detail. It is the bedrock of chemistry and ultimately of life as we know it. In our world, the molecules of life are almost exclusively left-handed. The amino acids that form every protein in your body are all left-handed versions. The sugar molecules that form the backbone of DNA are all right-handed. This uniformity is essential. It allows these complex molecular machines to fit together and function with precision. If you try to incorporate a right-handed amino acid into a protein chain built from left-handed ones, it is like trying to fit a right-handed glove onto a left hand. The structure fails. So, what happens in a universe where the fundamental handedness of particles is inverted? Mirror amino acids would likely be the opposite of ours. They would be right-handed. Mirror sugars would be left-handed. This creates a fascinating biochemical barrier. A mirror protein built from right-handed amino acids would be chemically incompatible with our left-handed biology. An enzyme from our world simply would not recognize or interact with a mirror molecule, and vice versa. This extends the separation beyond forces into the very language of chemistry. But does this flipped chirality prevent biology? Not at all. It simply means mirror biology would be built from the opposite set of molecular building blocks. A mirror cell would be just as viable and complex as one of our own, its internal machinery perfectly tailored to its own chiral consistency. The chemistry would be rich, dynamic, and capable of incredible complexity. It would just speak a dialect our instruments are deaf to. In fact, this profound difference might even be a necessity. If mirror molecules were not of opposite chirality, there might be rare, weak interactions between the sectors that could disrupt the delicate processes of life in both worlds. The chiral divide acts as a final, perfect insulation, ensuring that the two biospheres evolve in complete isolation. So, on a mirror Earth, forests might grow from trees built with mirror cellulose of the opposite twist. The scent of a mirror flower would be carried by mirror volatile compounds our noses could never detect. An entire symphony of biochemistry plays out, its notes tuned to a frequency of matter we can never hear, ensuring that even if we could somehow touch that parallel world, its very chemistry would render it as inert and alien as a stone to our biology. The profound silence between our world and its mirror is not merely a scientific curiosity. It is a blueprint for technologies that would seem like pure magic. If we could ever learn to isolate or even produce mirror matter, the applications would redefine the possible. The most immediate concept is the ultimate stealth. A vehicle or vessel coated with a layer of mirror matter would be completely invisible to any form of electromagnetic detection. Radar, LiDAR, infrared sensors, even the human eye would see straight through it. The coating would not absorb or reflect our photons, it would simply ignore them. The object would be a hole in space-time, detectable only by the faint gravitational shadow it casts, a whisper against the background hum of the planet. This is not camouflage, it is a fundamental disconnection from the spectrum of light we use to perceive our reality. Think of a submarine that does not hide in the ocean's depths, but instead phases into a different layer of the sea entirely, one where sonar pulses pass through it like ghosts. This leads to an even more revolutionary idea: gravity-based propulsion. We know the only bridge between the sectors is gravity. If we could engineer a device that manipulates or interacts with local concentrations of mirror matter, we might unlock a new form of movement. Picture a spacecraft that does not push against anything, but instead creates a gravitational gradient in front of it by influencing unseen mirror mass, literally falling forward through a gravity well of its own making. It would be a silent engine with no fiery exhaust, no roaring thrust, just a smooth, continuous acceleration powered by the hidden half of the universe. The energy requirements would be astronomical, and the engineering is currently the stuff of dreams, but the principle is rooted in that single, fragile connection between the two worlds. Perhaps the most haunting application is communication. If we could generate clean, modulated gravitational waves, we might be able to send signals into the mirror sector. These ripples in space-time would be the only language both realities could potentially share. A message encoded in gravity could pass through planets, through stars, through any ordinary matter barrier, carrying information across the cosmic silence. We could be broadcasting into the dark right now, unaware that our own planet's mass and motion are a constant, natural transmission. And if a mirror civilization exists, they might be doing the same. Our most sensitive instruments, like future generations of gravitational wave observatories, might one day pick up a pattern in the cosmic static, a sequence of pulses too orderly to be a collision of black holes, a first hello whispered across the divide of reality itself. The ultimate energy source might already be burning in a hidden dimension. If we could ever learn to ignite and control it, our entire civilization would be transformed. Picture a fusion reactor unlike any we can build today. In our world, the quest for fusion is a battle against plasma, a super hot soup of charged particles that desperately wants to escape its magnetic cage, touching the walls and instantly cooling. Containing that inferno is our greatest engineering challenge, but a mirror matter reactor sidesteps this problem entirely. The fuel would be mirror hydrogen, its nuclei fusing in a blistering ball of mirror plasma. This fire would be invisible to us, and here is the key, perfectly insulated by its own nature. The walls of our physical reactor chamber would be utterly meaningless to it. The mirror plasma could not touch them, could not transfer heat to them, because our atoms are deaf to its mirror electromagnetism. The only thing that could possibly contain this invisible sun would be gravity, or perhaps a magnetic field generated from within the mirror sector itself. Imagine a power plant where the core is a self-contained star hovering in a vacuum chamber, its light and heat forever trapped in a parallel reality. How then do we harvest its energy? We would not collect light or heat. We would tap the only bridge, gravity. The mass of that concentrated mirror fire would warp space-time. As the fusion reaction proceeds, the mass might fluctuate, or we could manipulate the mirror plasma to create controlled gravitational waves. These ripples in the fabric of reality could then be converted into electricity through methods we are only beginning to theorize, perhaps by moving massive superconducting loops in a carefully tuned dance with the gravity of the hidden flame. The reactor would run silently, with no radioactive waste from spent fuel in our sector, no risk of a meltdown in the conventional sense, because the fire itself could not physically interact with our world to contaminate it. It would be the cleanest, most contained power source imaginable, drawing from a well of energy that has been flowing beside us since the beginning of time. We would not be creating energy from nothing. We would finally be learning to listen to the hum of the other half of the universe and turning its silent song into light for our cities. A silent star dies in the dark. Across the cosmos, a massive mirror star, having burned through its hidden fuel, reaches its inevitable end. Its core collapses under its own immense gravity, and in a cataclysm of unimaginable force, it explodes. This is a mirror supernova. To our telescopes, the event is almost invisible. There is no brilliant flash to light up the galactic night, no expanding shell of glowing gas to paint a nebula across the heavens. The entire titanic release of energy is channeled into the mirror sector, a storm of mirror light and mirror particles that passes through our reality like a shadow. Yet no event of such violence can be completely contained. Two faint, ghostly signals might escape the hidden realm and cross into our own. The first is a burst of mirror neutrinos. Just as our supernova flood the universe with normal neutrinos, a mirror supernova would release a torrent of its own ghost particles. These mirror neutrinos, however, would pass through our planet and our detectors completely unnoticed, their presence marked only by a profound and inexplicable absence. The second signal is far more tangible: gravitational waves. The violent, asymmetric convulsions of the dying star's core would send powerful ripples through the fabric of spacetime itself. Since gravity is the shared bridge, these ripples do not care which sector they come from. They travel across the cosmic divide, carrying the fingerprint of the hidden explosion. This is where our most sensitive ears to the universe, observatories like LIGO and Virgo, come into the story. These facilities listen for the faintest tremors in space-time, the chirps and rumbles from colliding black holes and neutron stars. They have catalogued dozens of such events. But what if some of the signals they have captured do not perfectly match the expected profile of known collisions? A gravitational wave signal from a mirror supernova might look strange, its shape and duration slightly off, lacking the electromagnetic counterpart that astronomers desperately search for in the sky whenever a new gravitational wave alert sounds. It would be an orphaned ripple, a shout in the dark with no visible source. Scientists are already sifting through the data with this possibility in mind, looking for the unique gravitational signature of a solitary, collapsing massive object that does not fit the clean binary merger model. Finding one would be like hearing the echo of a thunderclap from behind a sealed door, definitive proof that a storm of unimaginable power is raging just on the other side of reality. That gravitational echo from a hidden supernova is not our only chance to hear the mirror world's birth cry. To find its true origin, we must look back to the very beginning, to the first light that ever traveled through the cosmos. This light is not the twinkle of stars, but a faint, cold glow that fills every corner of space, the cosmic microwave background. It is the afterglow of the Big Bang itself, a snapshot of the universe when it was just 380,000 years old, a fossilized imprint of creation's fiery dawn. This ancient radiation is our most powerful map of the early universe, and etched within its subtle patterns could be the faint signature of a twin. When our universe became transparent, releasing that first blast of light, the mirror universe would have undergone the same transition. As its own primordial plasma cooled, it would have released its own first light, a mirror cosmic microwave background. These mirror photons, forever invisible to our telescopes, would still carry the imprint of the mirror sector's initial conditions, its own unique pattern of density ripples and temperature variations. They fill the same space as our CMB, a second, ghostly image superimposed over the first. The question is, could we ever detect it? The only possible interaction is gravity. The mass and energy of that mirror photon bath would have contributed to the total gravitational landscape of the early universe. This means the distribution of ordinary matter that created our visible CMB patterns was likely nudged ever so slightly by the gravitational pull of the mirror sector's own evolving structures. Our map of the early universe might already include the subtle gravitational lensing effects of a hidden cosmos. But there is a more tantalizing possibility, a direct whisper. Some theories suggest there might have been a tiny, residual interaction between the two sectors in that ultra-hot, dense infancy, a fleeting connection that sealed shut as the universe expanded and cooled. This connection could have allowed a minuscule amount of energy or information to leak from one photon bath to the other. The result would be a specific, anomalous pattern in the polarization of the cosmic microwave background we observe. Polarization is the orientation of the light waves, and it carries detailed information about the physics of the universe's first moments. Precise measurements, like those from the Planck satellite and future observatories, are scanning this polarization with incredible detail, looking for signatures that defy the standard model of cosmology. A specific, unexplained twist in the polarization map could be the indelible fingerprint of that ancient conversation, the shadow of the mirror universe's first light cast upon our own. It would be a message from the other side, written in the geometry of the universe's oldest light, waiting for us to learn how to read it. The mirror universe is an idea of breathtaking elegance, but elegance alone does not make it true. In the rigorous world of physics, every beautiful theory must face a gauntlet of hard questions and inconvenient facts. The mirror matter hypothesis is no exception, and its critics point to several significant challenges. The most immediate is the charge of unnecessary complexity. Our standard model of particle physics, for all its quirks, is stunningly successful. It predicts the outcomes of experiments with incredible precision. Introducing an entire duplicate set of particles and forces, a complete shadow copy of reality, feels to some like a drastic solution. It doubles the fundamental ingredients of the cosmos without, so far, providing a single piece of direct, irrefutable evidence that this hidden sector exists. Why invent a whole new universe when we might just need one new particle? This leads directly to the second major criticism, the fine-tuning problem. For the two worlds to remain so perfectly isolated, the properties of the mirror particles must be exquisitely balanced. If their masses were even slightly different from their ordinary counterparts, or if the coupling strengths of their forces diverged, the delicate symmetry would break, and we might see stronger interactions between the sectors. The theory requires this near-perfect mirroring to explain the profound silence, and that feels, to some physicists, like an artificial and unlikely setup. It is a universe built on a razor's edge of mathematical coincidence. Furthermore, the mirror world has direct competitors in the quest to explain dark matter. For decades, the leading candidates have been particles like WIMP, weakly interacting massive particles. These are hypothetical entities within our own sector, far heavier than protons, that interact only through gravity and the weak nuclear force. They would be simpler, requiring no parallel forces or duplicate chemistry. Another favorite is the action, an ultra-light particle born from theories attempting to solve a different puzzle in quantum physics. These ideas are elegant in their minimalism, adding just one new ingredient to the cosmic recipe rather than an entire hidden kitchen. Given this landscape, why does mirror matter remain a compelling thought at all? Its power lies in its explanatory scope. It does not just propose a dark matter particle, it offers a reason for the broken symmetry we already observe. It ties together a fundamental puzzle in particle physics with the grandest mystery in cosmology. While WIMP and actions are elegant placeholders, mirror matter paints a richer, more complete picture of a symmetrical cosmos. It is a fringe idea, yes, but one that persists because it answers more than one question at a time. It dares to propose that the darkness holding galaxies together is not a simple substance, but a sign of a deeper, more profound structure to reality itself. The search continues not to prove the mirror world right, but to follow the evidence wherever it may lead, even if that path points toward a reality far stranger and more doubled than we ever dreamed. Our entire history of science is a story of expanding the real. We once thought Earth was the center of everything, then our sun was just one star among billions, and our galaxy one island in a vast cosmic ocean. Each discovery pushed the boundaries of reality outward, but the mirror universe proposes an expansion not outward in space, but inward in substance. It suggests the solid world you touch, the light you see, the very atoms you are made of, constitute only one facet of a dualistic cosmos. You are not at the center of the universe, but you may only be experiencing half of it. This is a philosophical shockwave that echoes ancient thought experiments and reshapes modern ones. Consider Plato's famous allegory of the cave, where prisoners see only shadows cast on a wall and believe those flickers are the whole of reality. We have always assumed the shadows were metaphors for our limited perceptions of this single universe. But what if the cave is far stranger? What if we are the shadows and another, equally solid world is casting its own light just beyond the wall? Our entire conception of what is fundamental, what is truly real, gets turned inside out. We are not just misreading the details of our world, we might be completely blind to an entire layer of existence that shares our address. This moves beyond simple curiosity into a profound challenge to materialism. If half of all matter is forever imperceptible, then our scientific instruments, no matter how advanced, give us access to only a partial truth. Observation, the cornerstone of the scientific method, is revealed to have a permanent blind spot. We can only ever see the universe tuned to our specific frequency. This forces a humbling admission: reality may be far richer and more layered than our senses or our science can ever fully capture. It connects directly to modern multiverse theories, but with a crucial difference. Many multiverse ideas propose separate, disconnected bubbles of space-time forever beyond our reach. The mirror universe is not separate, it is here. It is now, it is interleaved with every moment of your life. This is not a distant, abstract possibility, it is an intimate duality. The air in your room is also, potentially, the space through which mirror creatures move. The ground beneath your feet is to them as permeable as a ghost. Your body is a phantom passing through their solid world. This shatters any simple notion of objective reality. There is no single, authoritative stage. There are two overlapping stages, each with its own actors, each performing its own drama, neither aware of the other's script. So what does it mean for something to be real? Is it defined by what we can measure, or does reality exist independently of our perception? The mirror hypothesis leans toward the latter. It proposes a cosmos where the majority of existence operates on principles of tangibility and causality, just as robust as our own, yet remains forever hidden from our particular mode of observation. It suggests that real is not a binary condition, but a spectrum of interaction. A mirror rock is as real as granite, but only to the forces of its own world. To us, it is a gravitational whisper, a maybe. This transforms our place in the cosmos from being lonely explorers in a vast but knowable void to being inhabitants of a single room in an infinite mansion, listening for the faintest echoes of life in all the other darkened wings. This layered reality finds a natural home in the most ambitious map of the cosmos we have ever drawn, string theory. To make sense of the universe's deepest puzzles, string theory proposes that the fundamental ingredients of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy, strings. And for the mathematics of these strings to work, they must vibrate not in the 3 spatial dimensions we know, but in many more, perhaps 10 or 11. We are trapped like fish in a pond, perceiving only the surface of a far deeper reality. Where are these extra dimensions? They could be curled up or compactified at scales a billion times smaller than an atom. But another, more dramatic possibility exists. Some versions of string theory suggest that our entire 3-dimensional universe, with all its stars and galaxies, might be a 3-dimensional membrane or brain floating within a higher dimensional space. And we are glued to this brain. All the particles we know and love, and all the forces except gravity, are like paint stuck to the surface of this membrane. They cannot leave it. This is where the mirror world finds a breathtaking new interpretation. What if the mirror sector is not just a hidden frequency within our same space, but is painted onto a separate brain entirely? A parallel membrane, a ghostly sheet of reality, floating a microscopic distance away in a dimension we cannot point to. The particles of that world are just as stuck to their brain as we are to ours. This elegantly explains the profound isolation. The 2 worlds are not just tuned to different channels, they are playing on different stages that are stacked within the same grand theater. The only entity that can move freely between the stages, that can leak through the bulk of the higher dimensional space, is gravity. This is why it remains the sole bridge. In this picture, the mirror universe is not just hidden, it is literally in a different geometric layer of spacetime's architecture. The distance between our world and its twin might be less than the width of a proton, but it is a distance in a direction we cannot move or perceive. It is a separation written into the geometry of creation itself. A mirror planet does not phase through our Earth, it orbits in a parallel sheet, its gravity dimpling our shared spacetime from a fraction of a millimeter away in a 5th dimension. This framework transforms the search from one of particle physics into a test of cosmic geometry. If we could ever detect the specific, subtle ways that gravity behaves at microscopic scales, we might not just find extra dimensions, we might find the neighboring membrane where our cosmic twin resides. The broken mirror of 1956 was the first crack in the facade of reality. Qin Xiong Wu's Cobalt-60 experiment did more than prove the universe had a left-handed bias. It planted a seed of profound unease. For over 2 decades, physicists grappled with this lopsided cosmos, a universe that felt strangely imperfect. Then, in the late 1970s and early 1980s, a radical idea took root to restore that lost elegance. Theorists including Rabindra Mohapatra, Goran Senjanovic, and Robert Foote began publishing papers that asked, what if parity is not broken but hidden? Their work formalized the mirror matter hypothesis, proposing a complete duplicate set of particles and forces. This was no longer just a philosophical musing, it was a concrete, testable model of a parallel world. The elegance was compelling, but for years it remained largely a theoretical curiosity, a beautiful idea floating in the realm of mathematical possibility. The hunt for tangible evidence began in earnest in the 1990s as the tools of precision measurement caught up with the theory. Scientists realized the humble neutron might be the perfect spy, a particle that could potentially defect to the other side. This led to the first generation of high-precision neutron lifetime experiments in the late 90s and early 2000s. Teams using bottle traps and beam methods published their results, and a tantalizing discrepancy emerged. The lifetimes did not match, bottle experiments consistently reported neutrons disappearing about 9 seconds faster. While the numbers were close, 9 seconds was a chasm in this field of ultra-precision. It was the first potential whisper, a hint that neutrons might be vanishing into the mirror sector. This discrepancy ignited the field, transforming the mirror hypothesis from a fringe idea into a serious target for experimental physics. The 2000s and 2010s saw the pursuit become a global, high-stakes race. Laboratories around the world, from the Institut Laure Langevin in France to the Los Alamos Neutron Science Center in the United States, built ever more sensitive experiments. The goal was to crush the uncertainty, to measure the neutron's lifetime with such precision that any anomaly would stand out like a flare in the night. New techniques emerged, like using magnetic traps to hold ultra-cold neutrons in perfect isolation, or employing intense particle beams to count decay products with incredible accuracy. As the data improved, the original 9-second gap began to narrow, its statistical significance fading under the glare of better measurements. Yet the pursuit did not end, it evolved. The focus shifted from simply measuring the lifetime to probing the neutron's quantum behavior in exquisite detail, using tools like atomic clocks to detect the faintest wobbles in its magnetic properties that could signal an interaction with a hidden world. Today, in the 2020s, the search has entered a new phase of sophistication. Experiments are no longer just looking for missing neutrons, they are listening for the specific conditions that would make them disappear. Researchers manipulate powerful magnetic fields, theorizing that a mirror neutron would be influenced by a mirror version of that field. By tuning our magnetic environment and watching for changes in loss rates, they hope to catch the transition in the act. Simultaneously, the frontier has expanded beyond neutrons to antimatter. Projects at CERN are preparing to measure the magnetic properties of antiprotons with unprecedented precision, seeking any minuscule deviation that could be a fingerprint of an interaction with mirror forces. Each point on this decades-long timeline represents a step deeper into the unknown, a persistent effort to answer a single, haunting question. Are we truly alone in this universe, or is our reality just one reflection in a cosmic hall of mirrors? The clock is now ticking on a new generation of experiments designed to finally listen for that whisper. In the coming decade, 3 distinct frontiers will push our search for the mirror world from theoretical possibility into the realm of measurable fact. The first frontier remains the quietest, the hunt for vanishing neutrons. Next-generation experiments are moving beyond simply measuring lifetimes. They are constructing magnetic traps of unparalleled stability, seeking to directly observe the oscillation process itself. By applying carefully controlled, rotating magnetic fields, scientists aim to resonate with the quantum transition, effectively shaking neutrons and seeing if a fraction of them fall out of our reality in a predictable pattern. It is a bit like tuning a radio to a specific, unheard frequency. If the static suddenly drops, you know you have found the station. The goal is to achieve a sensitivity 100 times greater than today's best efforts, turning a subtle statistical anomaly into a clear, repeatable signal. Parallel to this, a second frontier searches for a potential messenger particle, a bridge that could carry a faint force between the worlds. Physicists call these hypothetical particles dark photons or hidden sector photons. The idea is that while our electromagnetism and mirror electromagnetism are separate, there might be a tiny, kin-like particle that can interact with both. A dark photon would be a cosmic intermediary, allowing a minuscule amount of energy or influence to leak across the divide. Dedicated experiments, like those planned at major particle accelerators, will blast ordinary matter with intense beams, looking for rare instances where energy seems to disappear, potentially carried away by one of these elusive dark messengers. Finding a dark photon would not prove the full mirror world exists, but it would be the first tangible evidence of a hidden sector, a crack in the door through which we might one day peer. The third and grandest frontier looks to the sky, to the silent collisions of the cosmos. Next-generation gravitational wave observatories like the planned Laser Interferometer Space Antenna, or LISA, will open a new window on the universe. LISA will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, laser-linked to detect the low-frequency ripples in spacetime that ground-based detectors cannot hear. This is the perfect frequency range to listen for the mergers of massive, compact objects. And here is the key: a collision between 2 mirror neutron stars would produce gravitational waves with a nearly identical signature to an ordinary merger. But with one glaring absence: there would be no accompanying flash of light, no gamma-ray burst, no glowing kilonova in any telescope across the electromagnetic spectrum. LISA and its Earth-bound cousins will work in concert with traditional observatories. When a gravitational wave chirp is heard, astronomers will immediately swivel every telescope they have to that patch of sky. If they see a brilliant explosion, it is a standard cosmic event. But if they see nothing, if the space-time ripple arrives alone, it could be the signature of a mirror universe catastrophe, a silent thunderclap from the dark. The next decade will be spent building these exquisite instruments, tuning them to listen for the echoes of a reality we have only ever imagined. So picture our own blue world, a sphere of rock and water bathed in sunlight. Now hold that image in your mind and layer over it an identical point in space. This is not an alternate dimension in a distant galaxy. It is a thought experiment rooted in the mirror matter hypothesis. What if a mirror Earth existed not just as a possibility but as a concrete fact? It would share our exact orbit around the Sun, a perfect gravitational companion, forever hidden in our own celestial shadow. The cosmic clock would be synchronized, our years and seasons passing in lockstep, a silent dance of 2 worlds occupying the same address. Yet the similarities might end with astronomy. Freed from the constraints of our geology, the mirror planet's surface could be a work of alien artistry. Where we have the vast Pacific, they might have a single, sprawling supercontinent. Our jagged Himalayas could be mirrored by gentle, rolling highlands. Their oceans might be shallower, their atmosphere thicker, a canvas painted by 4.5 billion years of independent, silent evolution. The true wonder, however, lies in the biosphere, driven by the same principles of natural selection but starting with a flipped molecular handedness. Life would have embarked on its own epic journey. Mirror ferns might have unfurled in primordial swamps, mirror dinosaurs could have ruled the land, and mirror primates might have descended from mirror trees. Their world could be a riot of unfamiliar colors, shaped by a chemistry that renders their flora and fauna invisible to our eyes, their scents undetectable to our noses. They might have cities or structures of such different purpose we would not recognize them as such. Their history, shaped by random asteroid impacts, volcanic events, and climatic shifts that never happened here, would be entirely their own. This leads to the most poignant question of the thought experiment. Could a mirror astronaut and a human ever truly meet? The heartbreaking answer is no, not in any way we understand as contact. They would be perfect ghosts to one another. If a mirror probe descended through our atmosphere, we would see no fiery streak. If it landed, it would settle onto the ground, or more likely, sink through it, coming to rest deep within the Earth's crust, held only by the faint mutual pull of gravity. A mirror explorer could walk through our walls, stand in the center of our rooms, and we would feel only the most imperceptible tug, a fleeting sense of extra weight in the air. We could shout and our sound waves would pass through them. We could shine the brightest laser and its light would ignore them completely. They would be surrounded by our solid world and we by theirs, 2 realities forever intertwined yet forever separate, each a phantom in the other's home. The only evidence of their existence would be the silent, steady gravitational pull of their entire planet, a force we already feel and call normal. In this scenario, we are already living on a world of ghosts, accompanied by an entire unseen civilization, sharing every sunrise and every orbit forever alone together. That silent companion, forever just out of reach, brings us to the end of an extraordinary journey. We began with a single broken mirror in a laboratory, a tiny bias in the spin of an electron that seemed to mar the perfection of the cosmos. From that one crack in reality's facade, we followed a thread of logic that led us to an entire hidden universe. The mirror matter hypothesis is not just another theory, it is one of the most profound what-ifs in all of science. It dares to suggest that every mystery, from the lopsidedness of particles to the dark glue holding galaxies together, might be a single clue pointing toward a reality doubled in on itself. This idea transforms our universe from a lonely stage into a shared space, a cosmic theater where two separate plays are performed simultaneously, their actors unaware of each other's presence. The search for this hidden half is more than a technical pursuit. It is a fundamental re-examination of what is real. Every ultra-precise neutron measurement, every scan of the ancient cosmic microwave background, every listening session for orphaned gravitational waves is an attempt to answer a deeply human question. Are we seeing everything that exists, or is our perception forever limited to one channel in a much grander broadcast? While the evidence remains elusive, the very pursuit expands the horizons of possibility. It reminds us that the universe is consistently stranger, more elegant, and more mysterious than our everyday senses suggest. The work continues in silent labs and in orbit around our sun, driven by a simple, powerful engine, curiosity. So what do you think? Does the idea of a parallel world of hidden particles, a silent twin to our own reality, feel like science fiction or a scientific inevitability? Share your thoughts on parallel worlds in the comments below. The greatest discoveries often begin not with an answer, but with the courage to ask a better question.